Okay, now I want to talk about something called conditional probability, which is the basis for a lot of what we're about to do with statistical machine learning and artificial intelligence. So I'd actually like to start with an example. Let's go back to the scenario we were thinking about with CS373 and CS477, except now let's look at the event space being over all students that are sinus. Let's say there's about 1,500 students that are sinus. And as we talked about, there are 22 students in this class, and there are 16 students in my other class, and 8 in common. Okay. Between the two. So now, if we think of the probability over an event space that includes all students and what they're taking, the probability of being in 477 or 373 goes down quite a lot. So let's say that this slightly bigger oval here is 477 in this Venn diagram, and the slightly smaller one is 373. And we know that we have this overlap here, right? So the probability now of being in CS477 has gone down a lot. If I pick any student at random, the probability that they're going to be in this particular class this semester is pretty small. And same thing for 373. So that's going to go down to 16 over 1,500. So those are pretty small. However, we can ask a slightly different question, which is, well, if I know that you're in CS373, what is the probability that you're in CS477? So let me write that out notationally. So we say this is called a conditional probability. So the probability that you're in CS477 given, so that's denoted by this vertical bar, given that you're in CS373. So it turns out this probability is going to be quite a bit higher than the probability of just any random or sinus student being in this class. So if I know you're in 373, that gives me a lot of information. To really understand this probability, what we have to do is look at the Venn diagram and think about what it's saying. So if I say you're in 373, I'm constraining myself to this part of the space, right? I'm saying you have to be in here. So if you're in there, how likely is it that you're in CS477? So what I can do is say, all right, let's think about just this yellow part of the space here. Those are the students that happen to be in CS373, but who are also in the 477 overlap here. And so what I really need to know is the proportion of this yellow area to the whole area in this oval here for CS373. So it's kind of like we've blown our whole event space up so that this is the Venn diagram inside of 373 here. And so we want to know, well, if I throw a dart inside of just the 373 region, how likely is it that it hits something in 477? So what we need to do is know, okay, what's the overlap between the two? And then what's the total number in 373? And we can answer this question. So if I write this out formulaically, what it's going to be is the probability that we're in CS477 and we're in CS373, which is the overlap, right? So it's the overlap divided by the constraint, the part of the space that we're constraining to. So the probability of CS373. Okay, so this is the formula for conditional probability. So in general, PA given B is equal to PA and B. Sometimes it'll just be written as a comma to say it's A and B over the probability of B. Okay. So if I look at the numbers we have here, what I see is, remember, we have an overlap of 8. So those students who are in both classes number in 8. So I'll say the probability of CS477 given CS373 is equal to 8 over the total number of students in 373, which is 16. Okay. Now actually, let me be a little more accurate here with this formula. Really what I'm saying is it's the probability of A and B in the whole space, so 8 over 1500, divided by the probability of B in the whole space. But what you see is that this denominator cancels out here, so it really is. You see it goes back exactly to our intuition of that we're constraining to this area and just counting the things that are there. So it ends up being 8 over 16, which is 0.5. So that's kind of interesting the way the numbers worked out. If you're in 373, you have a 50% chance of being in my AI class. So there's a pretty significant overlap there, which is neat. I'm very happy to have these students in both classes because sometimes we find synergy. Okay, let's look at another example of conditional probability. So this wouldn't be a probability discussion if we didn't bring up gambling at least once. So we're not really going to be talking about gambling much in this class, but it makes for a nice concrete example. So let's consider that we rolled 2 dice, and we wanted to know what the sum of the dice were. So ready? I'm going to fill in the sums. 1, 2, 3. All right, here it is. So we got a nice fancy Venn diagram. Every case is an individual cell in this space here. So let's consider what is the probability that the sum of the 2 die, so let's say die 1 plus die 2, is greater than or equal to 7, for example. So when I look at this, I can see that that should happen over half the time. I'll be very meticulous and count. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay. So there are, in total, 6 times 6 possibilities. So we saw that out of 36 possibilities, 21 of them came up to be a 7. So we see this is indeed slightly greater than half. But let's consider the conditional probability of, so if I back it up, let's say that it's greater than or equal to 7, but given that the first roll of the die is a 3. Well, so before it was, I'll write it down again just for our reference. Before, the probability was greater than a half, so it was 21 over 36. But now, we're constricting ourselves to this row here. So let me just box that row. And so in that row, now I have to count how many there are. So I see that there's actually 3 that are greater than or equal to 7. So 7, 8, and 9. So this ends up being 3 over 6. And again, another way I could look at that is the probability of rolling a 3 on the first die, and then rolling a 7, an 8, or a 9, that is 3 over 36. The probability of just rolling a 3 on the first die is 6 over 36. So anyway, I get the same thing, end up getting a half. Okay. I would expect the probability to be even lower if I rolled a 2 on the first one, right? So if I rolled a 2, it would be, let me do the full on probabilities here. So the probability of rolling a 2 is 6 out of 36. So I know I'm going to have that in the denominator. So remember, it's always the probability of, the joint probability, we call this, of the 2, divided by the probability of the thing we're conditioning on. So we're conditioning on that we've rolled a 2. And before we're conditioning on, we rolled a 3. So this is going to be in the denominator, and the numerator is the joint probability of having rolled a 3 on the first die and then rolling something that will lead to a sum that is greater than or equal to 7. So there's only 2 possibilities there. So 2 out of the 36 possibilities have both a roll in the first, roll of 2 in the first, and then rolling a second one, which leads to a sum that's greater than or equal to 7. So overall, this is actually 2 over 6, which is a third. So this matches our intuition. But just to show you, when you have a little more information about what you're looking at, that can change the probability that you have. Okay.